1.3 billion years ago, in a distant, distant galaxy, two black holes locked into a spiral, falling inexorably towards each other, and collided, converting 3 suns worth of stuff into pure energy in the 10th of a second. For that brief moment in time, the glow was brighter than all the stars in all the galaxies in all of the known universe. It was a very big bang. But they didn't release their energy in light. I mean, they're black holes. All that energy was pumped into the fabric of space and time itself, making the universe explode in gravitational waves. Let me give you a sense of the timescale at work here. 1.3 billion years ago, Earth had just managed to evolve multicellular life. Since then, Earth has made and evolved corals, fish, plants, dinosaurs, people, and even, God save us, the internet. And about 25 years ago, a particularly audacious set of people, Ray Weiss at MIT, Kip Thorne and Ronald Draver at Caltech, decided that it would be really neat to build a giant laser detector with which to search for the gravitational waves from things like colliding black holes. Now, most people thought they were nuts, but enough people realized that they were brilliant nuts that the US National Science Foundation decided to fund their crazy idea. So, after decades of development, construction and imagination, and breathtaking amount of hard work, they built their detector called LIGO, the Laser Interferometer Gravitational Wave Observatory. For the last several years, LIGO's been undergoing a huge expansion in its accuracy, a tremendous improvement in its detection ability. It's now called Advanced LIGO as a result. In early September of 2015, LIGO turned on for a final test run while they sorted out a few lingering details. And on September 14th of 2015, just days after the detector had gone live, the gravitational waves from those colliding black holes passed through the Earth. And they passed through you and me. And they passed through the detector.
There's 2 moments in my life that are more emotionally intense than that. One of them is the birth of my daughter. The other is when I had to say goodbye to my father when he was terminally ill. It was the payoff of my career, basically. Everything I've been working on, it's no longer science fiction.
So that's my very good friend and collaborator, Scott Hughes, a theoretical physicist at MIT, who's been studying gravitational waves from black holes and the signals that they could impart on observatories like LIGO for the past 23 years. So let me take a moment to tell you what I mean by a gravitational wave. A gravitational wave is a ripple in the shape of space and time. As the wave passes by, it stretches space and everything in it in one direction and compresses it in the other. This has led to countless instructors of general relativity doing a really silly dance to demonstrate in their classes on general relativity. It stretches and expands, it stretches and expands. So the trouble with gravitational waves is that they're very weak. They're preposterously weak. For example, the waves that hit us on September 14th, and yes, every single one of you stretched and compressed under the action of that wave. When the waves hit, they stretched the average person by 1 part in 10 to the 21. That's a decimal place, 20 zeros, and a 1. That's why everyone thought the LIGO people were nuts. Even with a laser detector 5 kilometers long, and that's already crazy, they would have to measure the length of those detectors to less than 1,000th of the radius of the nucleus of an atom. And that's preposterous. So towards the end of his classic text on gravity, LIGO co-founder Kip Thorne described the hunt for gravitational waves as follows. He said, "The technical difficulties to be surmounted in constructing such detectors are enormous. But physicists are ingenious. And with the support of a broad lay public, all obstacles will surely be overcome. Thorne published that in 1973, 42 years before he succeeded. Now, coming back to LIGO, Scott likes to say that LIGO acts like an ear more than it does like an eye. I want to explain what that means. Visible light has a wavelength, a size, that's much smaller than the things around you, the features on people's faces, the size of your cell phone. And that's really useful because it lets you make an image or a map of the things around you by looking at the light coming from different spots in the scene about you. Sound is different. Audible sound has a wavelength that can be up to 50 feet long. And that makes it really difficult, in fact, in practical purposes, impossible, to make an image of something you really care about, your child's face. Instead, we use sound to listen for features like pitch and tone and rhythm and volume to infer a story behind the sounds. That's Alice talking. That's Bob interrupting. Silly Bob. So the same is true of gravitational waves. We can't use them to make simple images of things out in the universe. But by listening to changes in the amplitude and in the frequency of those waves, we can hear the story that those waves are telling. And at least for LIGO, the frequencies that it can hear are in the audio band. So if we convert the wave patterns into pressure waves in air, into sound, we can literally hear the universe speaking to us. For example, listening to gravity, just in this way, can tell us a lot about the collision of two black holes, something that my colleague Scott has spent an awful lot of time thinking about.
If the two black holes are non-spinning, you get a very simple chirp. Whoop! If the two bodies are spinning very rapidly, I have that same chirp, but with a modulation on top of it, so it kind of goes... It's sort of the vocabulary of spin imprinted on this waveform.
So on September 14th, 2015, a day that's definitely going to live in my memory, LIGO heard this. So if you know how to listen, that is the sound of
two black holes, each of about 30 solar masses, that were whirling around at a rate comparable to what goes on in your blender.
It's worth pausing here to think about what that means. Two black holes, the densest thing in the universe. One with a mass of 29 suns, and one with a mass of 36 suns, whirling around each other 100 times per second before they collide. Just imagine the power of that. It's fantastic. And we know it because we heard it. That's the lasting importance of LIGO. It's an entirely new way to observe the universe that we've never had before. It's a way that lets us hear the universe and hear the invisible. And there's a lot out there that we can't see in practice or even in principle. So supernova, for example. I would love to know why very massive stars explode in supernovae. They're very useful. We've learned a lot about the universe from them. The problem is all the interesting physics happens in the core, and the core is hidden behind thousands of kilometers of iron and carbon and silicon. We'll never see through it. It's opaque to light. Gravitational waves go through iron as if it were glass. Totally transparent. The Big Bang. I would love to be able to explore the first few moments of the universe, but we'll never see them because the Big Bang itself is obscured by its own afterglow. With gravitational waves, we should be able to see all the way back to the beginning. Perhaps most importantly, I'm positive that there are things out there that we've never seen, that we may never be able to see, and that we haven't even imagined. Things that we'll only discover by listening. And in fact, even in that very first event, LIGO found things that we didn't expect. Here's my colleague and one of the key members of the LIGO collaboration, Matt Evans, my colleague at MIT, addressing exactly that.
The kinds of stars which produced the black holes that we observed here are the dinosaurs of the universe. They're these massive things that are old from prehistoric times. And the black holes are kind of like the dinosaur bones with which we do this archaeology. So it lets us really get a whole other angle on what's out there in the universe and how the stars came to be, and in the end, of course, how we came to be out of this whole mess.
Our challenge now is to be as audacious as possible. Thanks to LIGO, we know how to build exquisite detectors that can listen to the universe, to the rustle and the chirp of the cosmos. Our job is to dream up and build new observatories, a whole new generation of observatories, on the ground, in space. I mean, what could be more glorious than listening to the Big Bang itself? Our job now is to dream big. Dream with us. Thank you.